It came from outside. That is the first thing the instruments confirmed, and it is the thing that separates this object from every comet that has ever been named, tracked, and watched from the surface of Earth. It did not originate in the Oort cloud at the outer edge of our own solar system. It did not emerge from the Kuiper belt, that vast disk of frozen debris that marks where our solar system ends in the plane of the ecliptic. It came from interstellar space, from somewhere else, from a star system, or perhaps a region of space between star systems that formed before our sun existed, before our planets condensed, before the protoplanetary disk that would eventually become Earth had assembled enough mass to be considered a disk at all. The comet was named 3I, Atlas. The designation is precise. The 3 signifies that it is the third confirmed interstellar object ever detected passing through our solar system. The I signifies interstellar. Atlas is the name of the telescope network that found it first. The Asteroid Terrestrial Impact Last Alert System, funded by NASA, operating a ground-based observatory in Rio Hurtado, Chile. On the 1st of July 2025, the Atlas system logged a small speck of light moving against the background stars at a velocity and on a trajectory that could not be explained by any orbit originating in this solar system. The data was submitted to the Minor Planet Center. The orbit was confirmed. The object was interstellar. Tonight's report covers what happened in the months that followed that discovery, what a dozen NASA missions and multiple ESA spacecraft found when they turned their instruments toward this object, and what the research community has published in the months since it left. Because it has left. As of today, 3I, Atlas, is receding from our solar system on a hyperbolic trajectory at a velocity of 58 kilometers per second relative to the Sun. It will not return. The closest it will ever be to us again is where it is right now, tonight, as this report is filed. And it is already millions of kilometers away and moving outward. What it left behind is the record. And the record contains something that nobody who studies interstellar objects has seen before in an instrument dataset that is now publicly available in NASA's permanent archive. The specifics of what was found will be addressed in the briefing section, beginning with the Nature Astronomy paper published in the weeks leading up to tonight's report. That paper contains a number, a ratio, a measurement that describes the conditions in which 3I Atlas formed. And it is a number that appears in a different form in a documented ancient oral tradition that predates the construction of the observatory that found this comet by more than 1,000 years. Tonight's report also covers the historical parallel of what the only 2 previous interstellar objects designated, 1I, Oumuamua, and 2I, Borisov, revealed when they passed through, and what the 3I Atlas data adds to that picture. It covers what 6 separate ancient and oral traditions recorded when they observed unusual objects crossing the sky from beyond the expected regions of the cosmos. And it covers what the monitoring file on 3I Atlas, now complete, tells us about the nature of the universe that produced it. This channel files every night. We do not stop at the modern record. If this is your first time here, that is what we do. We take the science, cross it against the full depth of human observation, and present both without embellishment. The data is on the record. The interpretation belongs to you. If you find value in that, subscribe. New reports file every night. Tell us in the comments where you are watching from tonight. Tell us whether you were following 3I Atlas while it was still visible, and what you thought as it passed. The briefing begins now. Before we go further into the briefing, it is worth placing this object in context by explaining what our instruments could and could not tell us in the time available. 3I Atlas was a small nucleus. Estimates based on the Hubble Space Telescope observations range from approximately 300 meters to 6 kilometers in diameter, with the wide uncertainty reflecting the difficulty of separating the nucleus signal from the coma brightness in telescope data. This is a large range. The nucleus of Halley's Comet is approximately 15 kilometers in its long axis. The nucleus of Comet 67P Churyumov-Gerasimenko which ESA's Rosetta mission orbited for 2 years, is approximately 4 kilometers in its long dimension. 3I. Atlas may have been smaller than these, or it may have been comparable. We do not know the precise size. What we know is its composition, specifically what the ALMA measurements of its water tell us, and we know its trajectory and its velocity, and we know that it came from somewhere the solar system does not reach. The question of how it got here is itself a significant scientific subject. The interstellar medium is not empty. It is populated by clouds of gas and dust, by magnetic fields, by radiation from distant stars, and by objects like 3I, Atlas comets and asteroids ejected from their home star systems, by gravitational interactions, by close stellar encounters, by the dynamical processes that govern the evolution of any planetary system over billions of years. Our own solar system has ejected objects into the interstellar medium. The Oort cloud loses objects to gravitational perturbations by passing stars over geological timescales. Some fraction of those objects end up in the interstellar medium, traveling between stars until something intercepts them. 3I. Atlas is precisely such an object from another system intercepted by us. And the scientific question it poses: where did it come from? What was the environment that produced it? What does its chemistry tell us about the history of the galaxy? Is a question that the dataset it left behind in NASA's archive is now being used to answer. We continue to monitor what the data shows. And tonight, the data shows something worth the full depth of tonight's report. The discovery of 3I Atlas followed the established pattern for near-Earth object detection. The Atlas Survey Network, which operates telescopes in Chile, Hawaii, and South Africa as part of NASA's planetary defense infrastructure, conducts nightly wide-field scans of the sky looking for objects that move against the background stars in ways that indicate they are close to Earth. On the night of the 1st of July 2025, the Atlas CHL telescope in Rio Hurtado logged an object with a preliminary designation. The observation was submitted to the Minor Planet Center, the internationally recognized clearinghouse for small body position measurements operated under the International Astronomical Union. Within days, additional observations from telescopes around the world had confirmed the orbit. The orbit was hyperbolic. This is the critical measurement. An object originating in our solar system follows either an elliptical orbit, a closed path that brings it back around the sun on a predictable schedule, or a parabolic orbit, the mathematical boundary between closed and open. An object with a hyperbolic orbit is moving too fast to be gravitationally bound to the sun. It will never return. When the orbital calculations for 3I Atlas were run backward in time, the object's trajectory did not trace back to any recognized region of our solar system. It came from outside. The eccentricity of its orbit was measured at approximately 6.14, a number that is essentially unmistakable in its implication. Our sun's gravity cannot hold it. It is simply passing through. Here is the interactive hook for tonight's report. The Nature Astronomy paper published in the weeks before tonight's briefing documents the water composition inside 3I Atlas using data from the ALMA radio telescope array in Chile's Atacama Desert. The measurement is a ratio, the ratio of heavy water to normal water in the comet's coma. The specific finding is that 3I Atlas contains approximately 30 times more semi-heavy water molecules, in which one hydrogen atom has been replaced by deuterium, the heavier isotope than any comet originating in our own solar system has ever been found to contain. That ratio is a fingerprint of the conditions under which the comet formed. And that fingerprint, in a different language, appears in a documented oral tradition that was first recorded in writing in 1963 from Hopi elders, describing what happens when a blue star arrives from a region of the sky where no star should be. We will reach that connection before this report closes. Hold it. The closest approach of 3I Atlas to Earth was approximately 1.8 astronomical units, about 170 million miles, on its way inward toward perihelion. It was never a threat. The trajectory placed it at a distance equivalent to roughly halfway between Earth's orbit and Mars's orbit at its nearest point. Perihelion, the closest approach to the Sun, occurred on approximately October 29 to 30, 2025, at a distance of about 1.4 astronomical units, just inside the orbit of Mars. This is a critical piece of geometry because it determined which spacecraft could observe it and from what angles. NASA's Planetary Defense Network did not just detect 3I Atlas, it mobilized NASA's test satellite. The Transiting Exoplanet Survey satellite had actually captured 3I Atlas on camera in May 2025, weeks before its official discovery, in archival data that was identified retroactively. The Hubble Space Telescope observed it in early August 2025 and captured a dust plume being ejected from the sun-facing side of the nucleus as solar radiation began heating the fest object's surface. The James Webb Space Telescope, the most powerful infrared observatory ever deployed, observed the comet twice in February 2026 when its orbit had cleared the solar obscuration. NASA's Psyche spacecraft, en route to the asteroid belt, acquired 4 separate observations in September 2025. NASA's Lucy spacecraft, on its way to the Trojan asteroids, imaged the comet in a stacking sequence in mid-September 2025. The Europa Clipper, bound for Jupiter, trained its ultraviolet spectrograph on 3I Atlas in late 2025. The NASA Spherix mission, the spectrophotometer for the history of the universe, epoch of reionization and ICE's Explorer, conducted an infrared observational campaign in December 2025 that documented the comet's dust, water, organic molecules, and carbon dioxide in its coma. On the ESA side, Mars Express observed the comet as it approached perihelion. The ExoMars Trace Gas Orbiter contributed astrometric observations that helped refine the trajectory by a factor of 10. ESA's Jupiter Icy Moons Explorer, JUICE, also trained its instruments on the comet, and the data from JUICE arrived at ground stations in February 2026. The dual spacecraft UVS imaging published May 13, 2026. The result of both the JUICE and Europa Clipper instruments, simultaneously observing opposite hemispheres of 3I Atlas, is one of the most technically remarkable pieces of data in the entire observational archive. 2 spacecraft on opposite sides of the comet at different distances and different solar phase angles, imaging simultaneously. The result is a paired data set that constrains the comet's physical properties from multiple directions in a way that no single spacecraft observation could achieve. What all of these instruments found, collectively, is now on record. More than a dozen NASA missions observed this object. The full dataset has been placed in NASA's permanent public archives, where it is freely accessible. The University of Michigan team that published the Nature Astronomy paper used data from the ALMA array to measure the deuterium to hydrogen ratio in the comet's water, and the ratio they found is the number that matters most in tonight's report. 30 times more semi-heavy water than any solar system comet. That number will matter again before this report closes. One more piece of data to plant before we move to the historical parallels. The Origin study, led by researchers at the University of Michigan and published in May 2026, traces 3I Atlas's trajectory backward through the galaxy using stellar position data from ESA's Gaia mission, which has mapped the positions and motions of approximately 1 billion stars with unprecedented precision. Running the comet's trajectory backward in time reveals that it was not recently ejected from a nearby star system. It appears to have been traveling in the interstellar medium for an extended period, possibly billions of years. The researchers estimate it could be up to 11 billion years old, more than twice the age of our own sun. If that estimate is correct, 3I Atlas formed before our solar system existed. It has been traveling through the Milky Way for longer than Earth has been a planet. Keep that number in mind. 11 billion years. It will appear again before the ancient records section of tonight's report is finished. The mass of 3I Atlas is estimated at approximately 4.4 times 10 to the power of 10 kilograms, 44 billion kilograms. This is a rough estimate derived from the size estimate and an assumed density, and it carries the same uncertainties as the size estimate, but it provides a sense of scale. The comet's coma, the cloud of gas and dust that surrounds the nucleus as solar heating causes the ices to sublimate, was approximately 700,000 kilometers in diameter at its largest, according to observations from multiple instruments. That is nearly twice the diameter of the Sun. The coma extended in a tail driven by solar radiation pressure and the solar wind, producing the visible structure that telescopes tracked across the months of observation. The SPHEREX infrared observations, published by NASA in February 2026, documented the specific composition of the coma material. SPHEREX detected dust, water vapor, organic molecules, and carbon dioxide in the coma. The organic molecules detected include compounds that are relevant to prebiotic chemistry, the chemistry that, in the early solar system, may have contributed to the chemical inventory that eventually produced life. This finding is consistent with what was found in 2I, Borisov, and with the general expectation for cometary material from any origin, since molecular cloud chemistry tends to produce complex organics, but the specific combination in 3I, Atlas, combined with the D-H ratio from the ALMA measurement, places its chemistry in a formation environment that is more extreme than anything previously sampled from a passing interstellar object. The dual spacecraft ultraviolet imaging from May 2026, the joint Europa Clipper and ESA JUICE observation, provided the most geometrically complete picture of the comet's ultraviolet emission structure. Ultraviolet emissions from cometary comas are produced primarily by the photodissociation of water by solar ultraviolet radiation, which produces a characteristic emission from atomic hydrogen in the Lyman alpha wavelength. By observing both hemispheres of the coma simultaneously, the two UVS instruments produced a dataset that constrains the total water production rate, how much water vapor the comet was producing per second, more precisely than any single spacecraft observation could. This water production rate, combined with the ALMA-DH ratio, allows researchers to estimate the total mass of heavy water in the comet's original ice inventory. The numbers are preliminary and carry significant uncertainties, but the direction of the finding, significantly more semi-heavy water than any solar system comet, is robust. Multiple independent measurements converge on the same conclusion. There is a third specific piece of data from the 3I Atlas archive that tonight's report has not yet addressed and which connects to the historical record section, the non-gravitational force. In cometary science, non-gravitational forces are forces acting on a comet's nucleus beyond simple solar gravity. They arise primarily from the reaction force of outgassing when ice on the nucleus surface sublimates and jets of gas and dust are ejected into space. The nucleus experiences a small but measurable thrust in the opposite direction, the same principle as a rocket engine. For solar system comets, non-gravitational forces are well characterized and can be incorporated into orbital calculations. For interstellar objects, the situation is more complex because the object's composition and outgassing behavior may differ from what our models expect. For 1I, Oumuamua, the non-gravitational acceleration was anomalous and unexplained, too large to be explained by conventional outgassing from a cometary nucleus, and in the absence of a detectable coma, it spawned considerable scientific debate. For 3I, Atlas, the sky and telescope reporting as of late 2025 noted that non-gravitational forces were being carefully studied, but were not as anomalous as Oumuamua's. The JUICE and Europa Clipper astrometric data, combined with Earth-based astrometry, will be used to refine the non-gravitational force estimate in ongoing analysis work. The result of that analysis will further constrain whether 3I, Atlas's outgassing behavior, is consistent with conventional cometary physics, or whether it shows any anomaly comparably to Oumuamua's. As of tonight's filing, no significant anomaly has been publicly reported. The comet appears to have behaved in its outgassing as a comet should, which, given its extraordinary compositional properties, is itself a scientifically interesting finding. What the briefing establishes, before we move to the historical parallels, is this. 3I, Atlas, is a sample from the pre-solar epoch of the galaxy. It formed before our Sun. It traveled for possibly 11 billion years. It passed through our solar system, was observed by more instruments than any interstellar object in history, and left behind a data set that tells us something about the chemical history of the galaxy that we could not have known before it arrived. That is the event. That is what tonight's report is about. The story of how 3I Atlas came to be observed by more than a dozen separate NASA missions deserves its own section in tonight's briefing because it illustrates something important about the planetary defense infrastructure that we have built and how that infrastructure responded to the most significant interstellar visitor in the history of astronomical observation. The Atlas Survey Network is designed to find objects that might threaten Earth. It is not designed to find interstellar comets. But the design requirement for finding dangerous near-Earth objects, watching a wide field of sky with high cadence, flagging anything that moves fast and unexpectedly against the background stars, is identical to the detection requirement for any interstellar object entering the solar system. An interstellar object moves fast. It moves in an unexpected direction relative to the plane of the solar system. It appears and then moves in ways that ordinary solar system objects do not. The Atlas network flagged 3I Atlas because it was doing exactly what an interstellar comet does, and the algorithm that processes the Atlas data flagged it as something unusual and submitted the observation for human review and follow-up. Within days, the identification was confirmed by observatories around the world. What happened next was, by the standards of the planetary science community, remarkably coordinated. The James Webb Space Telescope, the most expensive scientific instrument ever built, with an observing schedule that is oversubscribed by a factor of roughly 5-to-1, was allocated time to observe 3I Atlas. This was not a routine process. Webb time is precious and allocated through a rigorous peer review system. But the scientific case for observing 3I Atlas was overwhelming. Only the third confirmed interstellar object in history, a compositional unknown, likely to be accessible for only a few months before fading beyond Webb's detection limit. Time was allocated. Webb observed the comet in August 2025, capturing images of its nucleus and coma at a level of detail that revealed the dust plume ejected from the sun-facing hemisphere. Webb observed again in February 2026, after the comet had passed perihelion and was receding, when its orbit allowed Webb to track it at longer wavelengths. Hubble, Webb's predecessor, and still one of the most productive observatories ever built, observed 3I Atlas in November 2025 from its vantage point in low Earth orbit. The Hubble observations captured the comet's coma structure and tail at optical wavelengths, providing complementary data to Webb's infrared view. The combination of Hubble optical imaging and Webb infrared imaging at different orbital positions of the comet is one of the most scientifically valuable instrument combinations in the 3I Atlas archive. Spherex, the spectrophotometer deployed earlier in 2025, conducted an infrared observational campaign in December 2025. Spherex observes the sky in 102 color bands across the near-infrared spectrum, and its wide field of view allowed it to track the extended coma structure of 3I Atlas during its December campaign. The Spherex data documented the chemical composition of the coma in its infrared spectral signature: dust with a specific grain size distribution, water ice bands, carbon dioxide emission, and organic molecular signatures. The Spherex dataset is particularly valuable because it represents a systematic, multi-wavelength characterization of the coma composition at a specific point in the comet's orbit, a snapshot of what the comet was doing in December 2025 that can be compared to observations from other epochs and instruments. NASA's TESS satellite, whose primary mission is to discover exoplanets by monitoring the brightness of stars over time, had captured 3I Atlas in its wide-field camera on May 23, 2025, nearly 6 weeks before the object was officially discovered by the Atlas telescope on July 1. This recovery observation was identified retroactively by searching the TESS data archive for fast-moving objects in the relevant sky regions after the comet's discovery. Confirmation. The TESS recovery data extended the observational arc for 3I, Atlas, by 6 weeks, which substantially improved the orbital determination and reduced the uncertainty in the computed trajectory. It also raised an interesting scientific question. If the TESS data archive contains observations of 3I, Atlas, from May 2025, what other interstellar objects might already be in the TESS archive waiting to be identified? The TESS database is publicly accessible, and researchers are actively searching it for additional recovery observations of 3I, Atlas, and for any evidence of other fast-moving transient objects that might be unidentified. Interstellar visitors. The two planetary science missions that made their observations of 3I, Atlas, from the outer solar system, NASA's Psyche spacecraft and NASA's Lucy spacecraft, represent a category of observation that could not have been made by any Earth-based instrument. From Earth's orbital position, 3I, Atlas, was observed at a specific viewing geometry, a specific combination of distance, phase angle, and relative motion. From Psyche and Lucy, positioned at different distances and different angles from the Sun and from Earth, the comet was observed at geometries that provide unique information about the structure and brightness distribution of the coma. The Psyche observations, made on September 8 and 9, 2025, from a distance of approximately 53 million kilometers from the comet, captured the coma in a multispectral imaging dataset that has been used to refine estimates of the comet's dust production rate and grain properties. The Lucy observations, made on September 16 from approximately 240 million miles away, captured the extended tail structure at a viewing geometry unavailable from Earth. The ESA complement to this multi-spacecraft observation campaign included 3 separate missions. Mars Express, orbiting Mars and equipped with instruments designed to study the Martian atmosphere and surface, contributed observations made when 3I, Atlas, was in the Mars neighborhood during its perihelion approach. The ExoMars Trace Gas Orbiter's Friend neutron spectrometer was directed toward the comet to search for neutron signals that might indicate hydrogen-rich material in the coma. The ExoMars astrometric data contributed to the trajectory refinement. ESA's JUICE spacecraft, the Jupiter Icy Moons Explorer, was the most distant of the ESA observers and contributed the simultaneous dual-hemisphere UVS imaging with Europa Clipper in May 2026. That is among the most technically remarkable observational achievements in the 3I Atlas archive. The total dataset assembled from this multi-mission observational campaign is now in NASA's permanent archive. More than a dozen distinct datasets from more than a dozen instruments, covering optical, ultraviolet, infrared, and radio wavelengths from Earth orbit and from beyond the orbit of Mars. The comet was observed for approximately 10 months, from its test recovery in May 2025 to the final Webb observations in February 2026, as it receded beyond convenient observational range. 10 months of observation of one object by the most sophisticated instrument suite in human history. The archive that observation produced will be analyzed by researchers for decades, used to constrain models of interstellar cometary chemistry, to refine understanding of cold molecular cloud environments, and to inform the design of future observational strategies for the interstellar objects that Rubin and future surveys will inevitably detect. The monitoring tradition that produced this archive, the systematic, multi-mission, internationally coordinated observation of an unusual celestial arrival, is the modern form of what the Babylonian astronomer priests were doing with their cuneiform tablets and their trained observers stationed across the ancient Near East. Different instruments, different institutional structures, different conceptual frameworks for understanding what the sky contains. The same fundamental practice: watch carefully, record precisely, make the record available for those who come after. The data is on the record. The interpretation belongs to you. To understand the significance of 3I, Atlas, it helps to understand how unexpected interstellar objects passing through our solar system actually are, and how unexpected the first two were when they appeared. The first confirmed interstellar object was 1I, Oumuamua, discovered in October 2017 by the Pan-STARRS Survey Telescope at the Haleakala Observatory in Hawaii. Oumuamua is a Hawaiian word meaning scout or messenger, from the far reach arriving first. The naming was prescient. 1I, Oumuamua, was unlike any comet or asteroid previously observed. It was highly elongated. Early estimates suggested an aspect ratio of approximately 10:1, though subsequent analysis has refined this, and it displayed an anomalous acceleration away from the Sun that could not be explained by solar gravity or by the normal outgassing behavior of a cometary nucleus. It produced no detectable dust coma, which is highly unusual for an object on a solar approach trajectory with cometary composition. Astrophysicist Avi Loeb, chair of Harvard's astronomy department, proposed in his 2021 book Extraterrestrial that the non-gravitational acceleration and unusual morphology of 1I, Oumuamua, were consistent with an object driven by solar radiation pressure, which in turn implied an extraordinarily thin and flat geometry, a light sail-like structure. This proposal was not adopted by the mainstream of the planetary science community, which developed alternative explanations centered on hydrogen ice, nitrogen ice, and photochemically altered surface chemistry. The debate was never conclusively settled because the object had already receded beyond observational reach before the necessary follow-up could be conducted. 1I, Oumuamua, was observed for approximately 11 weeks. No consensus explanation for its anomalous acceleration exists today. The second confirmed interstellar object was 2I, Borisov, discovered in August 2019 by amateur astronomer Gennady Borisov using his own telescope in Crimea. 2I. Borisov was in many ways the opposite of Oumuamua. It was unambiguously cometary in behavior, displaying a robust coma, a tail, and outgassing that behaved in the way a comet from our own solar system would be expected to behave. It was compositionally more similar to known short-period comets than 1I, Oumuamua, had been. The ratio of carbon monoxide to water in its coma was elevated compared to most solar system comets, but fell within the range of known solar system comets from the outer system. 2I. Borisov was large enough and bright enough that multiple major observatories tracked it over many months, producing the most complete dataset ever obtained on an interstellar object before 3I, Atlas. The significance of 3I, Atlas, in the historical context established by its two predecessors, is not simply that it is a third interstellar object. It is that it is significantly larger than either predecessor and compositionally distinct from both in ways that the scientific community did not predict. The ALMA water-deuterium ratio 30 times higher than any solar system comet places 3I, Atlas, in a formation environment far colder than any region of our solar system. This is not a marginal deviation. 30 times is a qualitative departure. The solar system's comets, including those from the outer Oort cloud at the coldest fringes of our sun's gravitational reach, formed in temperatures and under conditions that left a distinctive isotopic signature in their water. The signature in 3I, Atlas, does not match. It comes from somewhere colder, from a region where different chemistry operated. From outside, the publication of the Gaia-based origin study in May 2026, tracing 3I, Atlas's trajectory back through the galaxy, produced an estimate that has not yet been confirmed and carries significant uncertainties, estimates of the age and origin of an object on a hyperbolic trajectory through a galaxy in which billions of stars have moved significantly over billions of years, carry inherent imprecision. The researchers are explicit about this, but the best current estimate, derived from the best available data, places the object's origin in a cold, isolated region of the Milky Way that predates the formation of our solar system. The comet did not come from a recently active star system. It came from old space, from a region of the galaxy that had not yet condensed into its own star when our sun was forming. This is the historical context that defines what 3I, Atlas, represents. It is not simply a foreign visitor. It is a sample from the earliest epoch of the galaxy, a frozen record of pre-solar chemistry, an object that has traveled through the universe for a period longer than Earth has existed, carrying its original composition intact in the deep cold of interstellar space, and which passed close enough to our sun to be warmed, to develop a coma, to eject material into space, and to be analyzed by the most sophisticated instrument suite in human history. The European Space Agency's Comet Interceptor mission, currently in development, is specifically designed to observe a cometary object arriving directly from the outer solar system or from interstellar space before it has been significantly altered by solar heating. 3I, Atlas arrived before Comet Interceptor was ready, but its passage has provided the scientific argument for that mission's existence in a way that no theoretical discussion could have matched. It has demonstrated that interstellar objects arrive. They can be detected early enough for meaningful observation, and the science they contain is of a different order entirely from anything available in the objects we have been studying for centuries. The pattern in the modern record is clear, but we do not stop at the modern record. There is an older layer, oral traditions, documented prophecies, astronomical records, mythological texts that logged events matching this signature long before our instruments existed to confirm them. That layer is what comes next. The detection rate of interstellar objects passing through the solar system is a subject of active research and some debate. Before 1I, Oumuamua, was discovered in 2017, the theoretical expectation for the flux of interstellar objects was poorly constrained. There were no data points. After Oumuamua, after 2I, Borisov, after 3I, Atlas, the dataset still has only 3 members, which is a small sample for statistical inference. But even 3 detections in less than a decade, combined with the incomplete sky coverage of current survey telescopes, implies that the true rate of interstellar objects passing through the solar system is higher than the pre-Oumuamua theoretical predictions. This is a statement about detection efficiency as much as it is about the actual flux. Survey telescopes in 2017 covered a fraction of the sky with a fraction of the sensitivity they will have when the Vera C. Rubin Observatory reaches full operations. As the detection infrastructure improves, the detection rate will increase, and the question of whether that reflects an increase in actual flux or simply better coverage will take years of data to disentangle. What the 3 detections together suggest is that the interstellar medium is populated by objects at a density that makes it plausible, in principle, for a solar system to receive interstellar visitors at a rate of several per century detectable by current instruments, with the actual number, corrected for missed detections, possibly much higher. This has implications for what passes through planetary systems over billions of years and what chemical material those passing objects potentially deposit in the system they traverse. In the early solar system, when the sun was embedded in a dense star-forming cluster and the interstellar object flux was likely much higher than it is today, the chemical contributions of interstellar comets to the evolving planetary system may have been non-negligible. This scientific hypothesis that interstellar objects contributed chemistry to the early solar system is speculative in the current state of evidence. It is worth stating as a hypothesis with appropriate uncertainty because it is the kind of question the 3I Atlas dataset will be used to address, and because it connects the modern scientific investigation to the ancient questions about origin and arrival that the traditions covered in the ancient record section of tonight's report have always asked. The comparison with Oumuamua and Borisov is also worth extending in one more direction before the bridge. 1I. Oumuamua produced essentially no data on its composition. It was discovered too late, and its coma was too faint or absent for spectroscopic characterization. Its composition remains unknown except for the anomalous non-gravitational acceleration and the unusual morphology. 2I. Borisov was compositionally characterized and proved to be broadly cometary, similar enough to known solar system comets that it did not immediately upend assumptions about what the interstellar medium produces. 3. Atlas is now the best characterized interstellar object ever studied, and it has upended the assumption that interstellar objects will be compositionally similar to what we know from the solar system. It is not. The D-H ratio of 30 times higher than solar system comets is the single most significant compositional datum yet obtained from an interstellar object. It changes the picture. What it changes is the picture of what the galaxy's interstellar medium contains. If the cometary objects traveling between stars are, like 3I, Atlas, carrying chemistry from cold pre-solar molecular clouds with deuterium ratios far outside the solar system range, then the interstellar medium is not chemically uniform. Different objects in it carry the signatures of different formation environments. The galaxy is compositionally diverse at the level of individual comet nuclei traveling between stars. That is a profound and relatively recent scientific understanding made possible by the detection and characterization of 3 interstellar objects in less than a decade. It would not have been possible without the Atlas Survey Network, without the James Webb Space Telescope, without ALMA, without the multi-mission observational response that NASA and ESA assembled in the months between discovery and departure. The pattern in the modern record is clear. There is an older layer that saw this kind of arrival, named it, and kept the record. That layer is what comes next. The comparison between the 3 confirmed interstellar objects deserves more careful treatment before we move to the ancient record, because the contrast between them is what makes 3I, Atlas's compositional signature, scientifically significant. 1I, Oumuamua, arrived in October 2017 on a trajectory that led, when run backward, to the direction of the constellation Lyra, not to any specific star, but to a region of the sky that suggested an origin in a different part of the solar neighborhood. It was detected by the Pan-STARRS Survey Telescope at Haleakala Observatory in Hawaii on the 19th of October 2017, already past its closest approach to Earth and receding rapidly. By the time the scientific community recognized it as an interstellar object, it was already moving away. The window for observing it was short, approximately 11 weeks before it faded beyond detection. In those 11 weeks, astronomers used Hubble Space Telescope, the Very Large Telescope in Chile, the Keck Observatory, Gemini Observatory, and multiple smaller telescopes to characterize it as thoroughly as possible. The results were puzzling in ways that remain unresolved. Oumuamua showed no detectable coma, no cloud of gas and dust around its nucleus, despite being warmed by the sun during its perihelion passage inside the orbit of Mercury. Without a coma, spectroscopic characterization of its composition was limited to surface reflectance measurements, which showed a reddish color indicative of organic-rich or irradiated surface material, but gave no information about the interior composition. Most puzzling was the anomalous non-gravitational acceleration. After accounting for all known forces, solar gravity, radiation pressure from sunlight, and any outgassing that the detection limits of the observations could constrain, Oumuamua was accelerating away from the sun at a rate that could not be explained. Multiple explanations were proposed: hydrogen ice outgassing too diffuse to detect, nitrogen ice ablation producing non-gravitational force without visible coma, fractal dust aggregate geometry with unusually high surface area to mass ratio, and more exotic proposals involving manufactured structure. None achieved scientific consensus. The legacy of Oumuamua in the scientific literature is a benchmark of what we do not know about the interstellar object population. The first interstellar visitor was inexplicable. It was compositionally uncharacterized in any meaningful sense. Its behavior was anomalous. It departed without yielding a satisfying answer to any of the fundamental questions it posed. 2I. Borisov was different in almost every respect. Discovered by amateur astronomer Gennady Borisov on the 30th of August 2019, it was detected 2 months before its closest approach to the Sun, giving the astronomical community time to observe it while it was still brightening. Unlike Oumuamua, it displayed a robust coma from the start, a clear gas and dust cloud surrounding the nucleus, driven by sublimation of ices on the nucleus surface as solar heating increased. Spectroscopic observations confirmed the presence of cyanide, radical, diatomic carbon, and water. The carbon monoxide to water ratio in the coma was elevated compared to most solar system comets, but fell within the range of outer solar system comets. The nucleus size was estimated at approximately 500 meters. 2I. Borisov gave the scientific community its first compositionally characterized interstellar object, and the composition was, in broad terms, reassuringly familiar. An interstellar comet, the data suggested, could have broadly solar system-like composition. This was consistent with a hypothesis that cometary material from any planetary system would share broad chemical similarities, since the building blocks of star systems, hydrogen, carbon, oxygen, nitrogen, are the most abundant elements in the universe, and their chemistry under cold conditions tends to produce similar molecular inventories regardless of the specific star system involved. 3I. Atlas has substantially complicated that picture. The 30 times higher D-H ratio is not a minor deviation from what Borisov showed. It is a qualitative departure. The deuterium fractionation processes that enrich water and deuterium are sensitive to temperature. The colder the environment, the more efficiently deuterium is incorporated into water ice during formation. Borisov's D-H ratio, to the extent it was measured, was not dramatically different from solar system comets. 3I. Atlas's D-H ratio places its formation environment in a temperature regime substantially colder than the coldest regions of our own solar system. This is not a result of different stellar irradiation during a later warm period. The cometary nucleus preserves the original ice composition from the time of formation, insulated from subsequent thermal processing by its own bulk. The D-H ratio in the water ice is a record of the conditions at the moment of formation, preserved across however many billions of years the comet has been traveling. In the case of 3I, Atlas, that record is 11 billion years old. It is the oldest preserved chemical record ever directly measured by any instrument in human history. That is the full briefing context. 3 interstellar visitors in less than a decade, 3 completely different compositional profiles. A population of interstellar objects in the galaxy that is heterogeneous in ways that a 3-object sample cannot fully characterize, but that a 3-object sample is already revealing to be more diverse than theoretical pre-detection models anticipated. The monitoring picture points toward a galaxy whose interstellar medium carries the chemical signatures of many different formation environments, from many different epochs of the galaxy's history, in objects that travel between stars for timescales that dwarf the age of human civilization. The Hopi people of the Colorado Plateau have maintained a continuous oral tradition for more than 1,000 years on land they have occupied since at least the 12th century of the Common Era. Their agricultural communities in northeastern Arizona are among the oldest continuously inhabited settlements in North America. Their oral tradition encodes a detailed cosmological understanding of cycles, of sky, and of the arrival of specific signs that mark transitions in the great cycles of the world. The most significant of those signs in the Hopi tradition is the blue star Kachina. The blue star Kachina, known in the Hopi language as Sakwasohu, is described in the documented oral tradition as a blue star that will appear from a region of the sky where no star should be, arriving without the pattern of regular celestial motion that characterizes the known stars and planets. The tradition associates the blue star's arrival with the beginning of a period of great change, the transition from one world cycle to the next. It does not describe the blue star as a threat in itself. It describes it as a signal, a marker that has arrived to be seen and understood before the world changes in ways that the Hopi tradition has been preparing for. The primary documentation of the Hopi blue star Kachina tradition was compiled by Frank Waters in the Book of the Hopi, published in 1963 by Viking Press. Waters conducted his research over more than 3 years in direct collaboration with 30 Hopi elders from multiple clans across the Arizona Mesa communities, working with Oswald White Bear Fredericks as interpreter and collaborator. The book represents the most systematic documentation of Hopi cosmological oral tradition in the written record. The passages concerning the blue star Kachina prophecy are specific. They describe a blue-tinged celestial object that appears unexpectedly, that is not a planet following its known path, that brings its appearance near the beginning of the world-changing period, and that moves through the sky in a way that distinguishes it from the fixed stars and from the regular wanderers. The Hopi elders, Waters interviewed, described this tradition as having been passed down through many generations and as representing one of the most significant of the sky signs, encoded in their cosmological record. The relevance to 3i, Atlas, is not that 3i. Atlas was blue in the colloquial sense, though its spectral properties as measured by the Hubble Space Telescope did show a moderately blue color index consistent with fresh cometary material and a high albedo surface that reflected sunlight differently from the darker surfaces of most solar system comets and asteroids. The relevance is structural. The Hopi tradition describes an object arriving from outside the expected celestial order, not from the region where known stars and planets travel, but from elsewhere. An interstellar object on a hyperbolic trajectory arrives from exactly this direction relative to an Earth-based observer. It does not follow the ecliptic plane. It does not move the way the planets move. It comes from outside the established pattern of motion in the sky. Its trajectory, traced back, does not lead to any known region of the solar sky. It leads out of the solar system entirely, into the dark between stars. The Hopi tradition does not use modern orbital mechanics to describe what a blue star Kachina is, but the observational description of an object that arrives from where nothing like it has been seen before, that moves differently from every other object in the sky, and that carries within it some message or significance from a region beyond the ordinary sky. This is a structurally precise description of what an interstellar comet on a hyperbolic trajectory is. It does not come from where comets are supposed to come from. It arrives from interstellar space, outside the solar system, from a trajectory that no solar system object follows. The description is on the record. The object is on the record. The structural parallel is notable. Now to the Babylonian tradition, and specifically to the Enuma Anu Enlil, the great compendium of Babylonian celestial omen texts. The Enuma Anu Enlil is a series of approximately 70 cuneiform tablets containing thousands of omen texts derived from celestial observations made over centuries by the astronomer priests of Babylon and Assyria. The tablets were compiled in their canonical form approximately between 1500 and 700 BCE, though they draw on observational traditions extending further back into the 3rd millennium before the Common Era. The standard scholarly edition has been analyzed across generations of Assyriologists, with major contributions from scholars including Erika Reiner, David Pingree, and Hermann Hunger, working at institutions including the University of Chicago Oriental Institute and the Austrian Academy of Sciences. The sections of the Enuma Anu Enlil most relevant to tonight's report are the tablets devoted to cometary and atmospheric phenomena, what the Babylonian scribes called interchangeably stars that fall and stars of the night sky that are not of the regular pattern. The Babylonian astronomical tradition was sophisticated enough to distinguish between the regular wandering stars, what we now call planets, and the irregular phenomena, comets, meteors, novae, and other transient events. The omen texts are organized around the observed characteristics of these phenomena: their color, their direction of motion, their direction of tail, their brightness relative to known stars, and their position in the sky relative to constellations associated with specific regions and nations. For cometary phenomena, specifically, the Enuma Anu Enlil tablets record observations of objects moving through the sky against the regular motion of the stars, objects that develop tails pointing away from the sun, objects that vary in brightness over days and weeks, and objects that appear in regions of the sky where no regular celestial body had been observed before. The omen texts associated with such objects range from interpretations tied to specific political events to more general statements about disruptions in the cosmic order. But the underlying observational practice, the recording of an unusual sky object's appearance, motion, direction, and characteristics, is systematic and precise by the standards of pre-telescopic astronomy. What the Babylonian tradition lacked was the concept of an interstellar origin. Within the Babylonian cosmological framework, all celestial objects occupied the dome of heaven between the earth and the fixed stars. There was no space beyond the stars in the Babylonian model of the cosmos. An object arriving from outside the solar system would have been categorized within the existing observational framework as an unusual star, a moving phenomenon. A celestial sign and its characteristics would have been recorded with the same precision applied to any other celestial event. The Enuma Anu Enlil tablets demonstrate that Babylonian astronomical observers were precise enough to record the color, direction, and motion of cometary phenomena with enough specificity that modern scholars can identify specific historical events, including the appearance of Halley's Comet at historically datable returns in the cuneiform record. 3I, Atlas, had it appeared bright enough to be visible to the naked eye, would have entered the Babylonian observational record as an object of specific, ominous significance, moving from a direction outside the ecliptic, developing a coma and tail observable to the eye, and then receding back into the sky from which it came within weeks. An object matching this description appears in cuneiform records from multiple periods. Whether any of those objects were interstellar in origin is not known and cannot currently be determined from the omen texts alone. What can be said is that the Babylonian observational framework was sensitive enough to detect such an object and systematic enough to record it in detail. The observational tradition was real. The records are real. The infrastructure for detecting what 3I, Atlas, was exists in the ancient record, even if the conceptual framework for naming what it was does not. The Norse cosmological tradition, encoded in the Eddas, the poetic Edda, compiled in Iceland in the 13th century from older oral tradition, and the prose Edda, written by Snorri Sturluson, approximately 1220 CE, contains a specific cosmological element that bears on tonight's report. The Norse cosmos, as described in the Eddas, is divided into 9 worlds arranged on a cosmic structure called Yggdrasil, the world tree. The outermost of these worlds, the region beyond the ordered cosmos, is Utgard, the outer region, the space beyond the walls of the worlds. In the Norse framework, things from Utgard are fundamentally other. They do not follow the rules of the ordered cosmos. They are not subject to its governance, and when they enter the ordered worlds, they bring disruption. The most relevant specific element for tonight's report is the account in the Völuspá, the first and most significant poem in the poetic Edda describing the cosmic dissolution called Ragnarok. In the Völuspá, among the signs of the coming dissolution, stars fall from the sky. But the specific formulation in several stanzas describes stars that are not of the regular pattern objects that move against the established order of the sky. The Norse cosmological tradition does not distinguish between comets and meteors in the modern sense, but it does distinguish between the regular motion of the known celestial objects and the irregular arrival of things from beyond. The fire from beyond the sky, associated with the figure of Surtur from Muspelheim. The realm of fire at the edge of all things is specifically fire that originates outside the ordered cosmos and arrives to consume what is within it. An object of interstellar origin is literally fire from beyond the ordered sky. Its chemistry, in the case of 3I, Atlas, chemistry that formed in conditions colder than anything in our solar system, and which includes complex organic molecules documented by the Spherex infrared data, is chemistry from outside the solar system that has now, however briefly, entered our cosmic neighborhood. It arrived from Utgarder in the cosmological sense. It does not follow the rules of the orbital mechanics that govern every other object our sky contains, and it has now returned to the dark from which it came. The Eddas are not describing an interstellar comet in the language of modern astrodynamics, but the cosmological framework they encode, the radical distinction between the ordered cosmos, whose objects follow known paths, and the outer realm from which things arrive that do not, is a conceptual framework that maps onto the distinction between solar system objects and interstellar objects with considerable precision. The order of the solar system is its orbital mechanics. Everything in it follows predictable paths governed by the sun's gravity. 3I, Atlas did not. It came from the outer space, and it has returned to the outer space. In cosmological terms, in the Norse framework, and in several others, this is precisely the distinction that matters. Now to the Chinese guest star tradition. The Chinese imperial astronomical tradition, maintained continuously through the dynastic histories from the Han Dynasty onward, includes one of the most systematic records of unusual celestial phenomena in the ancient world. The Tianwenji sections of the official dynastic histories, the treatises on celestial phenomena, document what Chinese astronomical observers called Keixing, meaning guest stars. Stars that appear where no star had been before, and then disappear. The term encompasses what modern astronomy classifies as novae, supernovae, comets, and in some cases, bright meteors. The Chinese guest star tradition is most famous for its record of what is now identified as the 1054 CE supernova that produced the Crab Nebula, a guest star documented in the Songxi Times as appearing in the constellation Tianguan in July 1054, visible in daylight for approximately 3 weeks, and visible at night for nearly 2 years. This record allowed modern astronomers in the 20th century to definitively identify the Crab Nebula as the remnant of a stellar explosion observed and documented in China 9 centuries earlier. This is the most celebrated example of the Chinese astronomical record's utility for modern science. But it is not the only one. The Chinese records also contain systematic documentation of cometary phenomena extending back more than 2,000 years, with observations recorded including direction of motion, color, length and direction of tail, and duration of visibility. The Jinshu, the history of the Jin dynasty compiled in the Tang period, includes descriptions of comet observations from the 3rd and 4th centuries CE that modern researchers have cross-referenced with calculated orbital returns of known periodic comets. The reliability of these records is sufficiently established that they are used as primary data sources in the computation of historical comet orbits. Within this tradition, an object moving against the ecliptic, arriving from a direction outside the normal paths of the planets and known comets, would have been noted, classified, and interpreted within the omen framework of the tradition. Chinese astronomical omens associated with cometary appearances that moved from unexpected directions toward the emperor's regions of the sky were considered especially significant. The direction of motion and the region of sky entered were both recorded because both were considered interpretively relevant. An object arriving from a direction that placed its origin outside the regular celestial framework would have been classified as a particularly significant guest star, its appearance interpreted within the political and cosmic framework of the period. 3I, Atlas was not visible to the naked eye. Its closest approach to Earth kept it too faint for ancient observation, but the systematic tradition of recording and interpreting unusual sky phenomena that the Chinese astronomical observers maintained for 2,000 years is the oldest institutional expression of what modern planetary defense represents. A systematic, state-sponsored commitment to watching the sky and recording what arrives from it, because what arrives from it matters. The Atlas survey network that found 3I, Atlas, the wide-field telescopes that monitor the sky continuously for fast-moving objects, the Minor Planet Center that coordinates the global observational response. These are the modern institutional form of the same fundamental practice. Watch the sky, record what you see, interpret what you find. Now to the answer to the interactive hook posed in the briefing section. The Nature Astronomy paper documents that 3I, Atlas, contains 30 times more semi-heavy water in which one hydrogen atom is replaced by deuterium than any comet originating in our solar system. This D-Ha ratio, the deuterium to hydrogen ratio in the comet's water, is the primary compositional fingerprint linking the comet's formation environment to a specific type of interstellar chemistry. High D-H ratios in water indicate formation in extremely cold environments, where deuterium fractionation processes concentrate the heavier isotope in water ice. The colder and more isolated the formation environment, the higher the DH ratio in the resulting water ice. 30 times higher than solar system comets places 3I. Atlas's formation environment in what astrophysicists call a cold, dark molecular cloud, a region of interstellar space so cold and so dense that it has not yet collapsed into a star, where temperatures approach 10 Kelvin within a few degrees of absolute zero. These are the coldest known natural environments in the observable universe. They are the birthplaces of stars, the reservoirs from which protostars and protoplanetary disks form when gravitational collapse eventually occurs. 3I, Atlas, did not come from a star system. It came from a molecular cloud, perhaps one that never formed a star, or one whose star formed long ago and left the comet as an orphan in the interstellar medium. The 11 billion year age estimate means this object formed before the Milky Way had assembled most of its current stellar population. It is older than the disk of the galaxy that contains our Sun. It traveled through interstellar space for a period longer than Earth has existed, and then passed through our solar system in approximately 8 months, from discovery to the limit of observability, leaving behind a dataset that will be analyzed by researchers for decades. The Hopi blue star Kachina tradition describes an object arriving from outside the established pattern of the sky that carries within it the signal of a transition, carrying a message from a time before the current world order began. The description, in Frank Waters' documentation, working from the oral accounts of the Hopi elders, is specific enough to be notable in this context. The blue star comes from a place where the ordinary rules of sky motion do not apply. It is not a planet. It is not a regular star. It arrives from outside, and its arrival marks a change. The deuterium fingerprint of 3I Atlas marks precisely this. It is literally from a time before the current order of the solar system. It carries chemistry from before our sun formed. It is an emissary, in material terms, from the epoch that preceded everything we know as the solar neighborhood. This is not a proof of anything beyond the object's physical chemistry. The Hopi tradition was not predicting 3I, Atlas. The description recorded by Waters in 1963 from the Hopi elders cannot be taken as a precise astronomical forecast. What it can be taken as is a cosmological observation, an encoding in the language of oral tradition of the recognition that objects arrive from outside the sky's known order, that such arrivals carry significance, and that their chemistry and their origin are from a different time and a different place than everything else in the observable sky. The Nature Astronomy paper says the same thing in the language of deuterium fractionation and molecular cloud chemistry. The parallel is structural. The data is on the record in both places. The description recorded in 4 separate ancient and oral traditions is structurally identical to the data on the board tonight. The Hopi oral tradition names the arrival of a sky object from outside the established order and associates it with the transition between cosmic epochs. The Babylonian Enuma Anu Enlil establishes the institutional practice of observing and recording sky objects that do not follow the established pattern of celestial motion, and preserves observations that match the profile of what interstellar objects would look like from the ground. The Norse Eddas encode the cosmological distinction between the ordered sky and the outer realm from which objects arrive that are not of the ordered sky, a distinction that maps precisely onto the distinction between solar system objects and interstellar objects. And the Chinese guest star tradition represents the oldest continuous institutional commitment to systematically recording and interpreting unusual celestial arrivals, a tradition that would have classified 3I, Atlas, as a guest star of extraordinary ominous significance had it been visible to the naked eye. The data is in the record. The interpretation belongs to you. The Norse tradition requires one more layer of examination to make the structural parallel fully clear. The Veluspa, the prophecy of the seeress, the first and most cosmologically complete poem in the poetic Edda, describes the creation of the cosmos, the ordering of time and space by the Aesir gods, and the eventual dissolution of that order in Ragnarok. The poem is structured as a vision from the distant past to the distant future, delivered by a vulva, a prophetess, who has witnessed the ordering of the cosmos from its beginning and who sees its end. The cosmological vision encoded in the Voluspa is not a simple narrative of divine conflict. It is a systematic account of how the ordered cosmos is constituted and how it comes apart. The specific stanzas relevant to tonight's report describe the signs that precede Ragnarok: stars falling from the sky itself splitting, fire from beyond. The Norse word used in several Eddic contexts for the region from which fire approaches from beyond is Muspel or Muspelsheim, the realm of primordial fire that existed before the ordered cosmos was made, and that exists at the outer boundary of the ordered cosmos now. In the Norse cosmological framework, Muspelsheim is not simply hell or destruction in a generic sense. It is the outer fire, the primordial energy that predates the world tree and the ordered cosmos, that was there before the gods made the worlds, and that will be there after they are gone. The beings of Muspelsheim, led by Surtur, arrive at Ragnarok from outside. They cross the bridge Bifrost, which cracks and breaks under their weight, and they arrive in the ordered worlds from the outer realm. This cosmological geography, an ordered cosmos, with well-defined rules of motion and composition, surrounded by an outer realm from which things arrive that are not of the order, is precisely the cosmological geography that interstellar object science has now confirmed in empirical terms. There is a solar system with well-defined orbital mechanics where everything follows the rules of solar gravity and planetary perturbation. And there is the interstellar medium, which is not part of the solar system's ordered structure, from which objects like 3I, Atlas, arrive on hyperbolic trajectories arriving from outside, following their own rules, carrying chemistry from an era before the solar system existed, and then returning to the outer realm from which they came. The Eddas are not science, but they are systematic observations about the structure of the cosmos embedded in a mythological framework, and the structural observation they encode that there is an ordered inner realm and an outer realm from which things arrive that are not of the inner realm is an observation that thousands of years of celestial observation by Norse and before them Proto-Germanic peoples had produced from watching the sky carefully. The distinction between objects that follow the regular cycles of the sky and objects that arrive suddenly from unexpected directions is an observational distinction that ancient skywatchers in every tradition noticed and tried to name. The Norse named the outer realm Muspelsheim. The Babylonians called unusual sky phenomena signs from Anu, the sky god, whose domain was above the regular celestial order. The Hopi called the arrival from outside the blue star's domain. The Chinese called such visitors guest stars, stars that had not been there before and would not remain. Modern science calls them interstellar objects. The naming is different. The observation is the same. There is one more element of the ancient record to examine tonight, and it connects directly to the number that has run through this report: 11 billion years. The estimate that 3I, Atlas, formed before our sun in a cold molecular cloud that predates the solar system places the object in a temporal category that is almost impossible to hold in human intuition. 11 billion years ago, the universe was approximately 2 to 3 billion years old. The Milky Way galaxy had formed, but its current structure was still assembling. Most of the stars in the galaxy today had not yet formed. The cold molecular cloud in which 3I, Atlas, appears to have originated may have been one of the earliest sites of cometary chemistry in this region of the galaxy. It is possible, not established, but possible that the material in 3I, Atlas, is among the oldest solid matter that has ever been sampled by human instruments. The Babylonian astronomical tradition that produced the Enuma Anu Enlil was operating in what, by any human measure, seemed like a very long tradition. The Enuma Anu Enlil draws on observational records extending back to the 3rd millennium BCE, 5,000 years of systematic sky watching, a span of time that is, by human standards, almost incomprehensible. And yet, 5,000 years is to 11 billion years what a single heartbeat is to an average human lifetime. The object that passed through our solar system and left in 8 months carries within it the chemical record of a duration that makes the entirety of human civilization, including all the skywatching and all the tradition and all the accumulated knowledge, seem like a rounding error. This is not a statement intended to reduce the importance of the human record. The human record of sky watching across 5,000 years of Babylonian tradition, 1,000 years of Hopi oral transmission, 1,000 years of Norse cosmological encoding, 2,000 years of Chinese guest star recording. That record is precious precisely because human beings have a finite time and a finite vantage point from which to observe. What they observed and preserved is irreplaceable. But the temporal context of 3I, Atlas, arriving from 11 billion years of solitary travel through the galaxy, places the question of who is watching and who has been watching, and for how long, in a perspective that the ancient traditions, in their own way, also addressed. The Hopi cosmological tradition describes cycles within cycles, worlds within worlds, time spans that dwarf human memory. The Babylonian tradition invoked the primordial ordering of the cosmos as the framework within which their omen interpretations operated. The Norse Eddas describe a cosmos whose beginning predates the current world by an undefined but vast span. The Chinese astronomical tradition was self-consciously placed within an imperial framework that claimed continuity from the first sage kings, a horizon of legitimacy extending into mythological time. In all of these traditions, the sky-watching practice was connected to a recognition that the sky contains objects and events from times far beyond human memory. The guest stars that appeared and disappeared in the Chinese records were, in some cases, explosions of stars that had happened thousands of years before the light reached Earth. The Norse outer fire that approaches from Muspelheim is, in the cosmological framework, a force from before the ordered cosmos from before time in some readings. The Hopi blue star comes from a region beyond the known sky. All of these traditions are, in their different ways, gesturing at the recognition that the cosmos contains things from a time before human observation began, and that those things arrive, occasionally, in the observable sky. 3I, Atlas arrived. It was from 11 billion years ago. It was from a cold, dark, molecular cloud in the early galaxy. It passed through our solar system in 8 months and left. It will be in the interstellar medium again in a few years. We observed it with instruments that no previous generation possessed. The record it left is in a publicly accessible archive. The data is on the record. The interpretation belongs to you. The question of how human cultures have consistently developed frameworks for understanding the arrival of things from outside the expected order of the sky is worth examining in one more dimension before the report moves to its closing section. The 4 traditions covered in tonight's report, Hopi oral tradition, Babylonian Enuma, Anu, Enlil, Norse Eddas, Chinese guest star records, are geographically, linguistically, and chronologically diverse. They share no direct historical connection. They were developed independently on different continents, in different languages, over different centuries, by people who had no knowledge of each other's existence. And yet all 4 arrived at broadly similar observations, that the sky occasionally produces arrivals that do not fit the established order of celestial motion, that these arrivals deserve to be observed carefully and recorded precisely, and that they carry significance that transcends the ordinary. The explanation for this convergence is not supernatural, it is observational. Human beings who watch the sky carefully over many generations notice the same phenomena. Comets appear and disappear. Bright new stars novae flare up and fade. Objects move across the sky in ways that distinguish them from the regular motion of the planets and the fixed stars. Any culture that watches the sky systematically will notice these anomalies and will develop some framework for naming and interpreting them. The frameworks differ. The observations underlying them are the same, because the sky produces the same phenomena for every observer on Earth, regardless of culture or century. What is notable about 3I, Atlas specifically, is that it represents a category of phenomenon, the interstellar visitor, that the ancient traditions could only partially access. Without telescopes, the faint nucleus of an interstellar comet at 3I, Atlas's closest approach, would have been invisible to the naked eye. Atlas, 3I, Atlas was never naked-eye visible. It required modern instrumentation to detect, and yet the conceptual category it represents, an object arriving from outside the solar system's ordered structure, was independently developed by multiple ancient traditions as a cosmologically significant class of event. They did not see 3i, Atlas, or objects like it directly in most cases. But they saw the sky well enough to recognize that it sometimes produces things that do not fit the established pattern, and they built frameworks around that recognition. The Babylonian tradition is particularly relevant here because of its systematic character. The Enuma Enlil is not a collection of folk observations. It is a professional astronomical text, maintained by a specialized class of observers whose social function was precisely to observe, record, and interpret unusual celestial phenomena. The astronomer priests of Babylon and Assyria, the Tupshar Enuma Enlil, describes of the Enuma Enlil, were professionals in the same sense that modern planetary scientists are professionals. They had training, institutional affiliations, reporting obligations, and a body of accumulated knowledge that they built upon and transmitted to successors. The Enuma Enlil is the cumulative product of centuries of professional astronomical practice. When modern scientists, like those at the Atlas Survey Network, observe the sky every night and report unusual objects to the Minor Planet Center, they are operating in the same professional tradition, systematically watching, systematically recording, systematically reporting, even though the specific concepts and instruments are incomparably more sophisticated. The Hopi tradition operates differently, transmitted not through professional institutions, but through the kinship and clan structures of the Hopi community, through ceremonial contexts in which cosmological knowledge is rehearsed and preserved, through the Kachina tradition in which aspects of the cosmic order are embodied and performed. The knowledge is no less precise for being transmitted this way. The multi-generational observational record of the Hopi skywatchers, accumulated across a millennium of occupation on the Arizona mesas, is encoded in the traditions that Frank Waters and the Hopi elders documented. It is a different kind of archive from the cuneiform tablets, but it is an archive. The Norse tradition is different, again embedded in a literary and poetic form, in the alliterative verse of the Eddic poems, where cosmological observation is encoded in narrative and metaphor. The precision of the Norse tradition lies in its structural mappings, the relationships between the ordered and the outer, the known and the unknowable, the cyclic and the terminal. It is a cosmological architecture rather than an observational record, but it is built on the same recognition. The sky produces arrivals from outside, and those arrivals are significant. These are the 4 archives that tonight's report has placed alongside the 3i, Atlas dataset. They are all real. They are all accessible. They all contain, in their different forms, the recognition that the cosmos occasionally sends objects from outside the expected order of the sky. The modern dataset for 3i, Atlas, tells us what those objects are in physical terms: their composition, their origin, their trajectory, their age. The ancient archives tell us what human beings have made of such arrivals across the full span of recorded history. Both records are worth keeping. Both deserve to be read. There is one more ancient text that deserves examination tonight before this report closes the ancient record section. The Book of Enoch, specifically the astronomical book section known as 1 Enoch chapters 72 to 82, is one of the oldest surviving texts in the Hebrew apocalyptic tradition and one of the earliest systematic attempts in the Jewish textual tradition to describe the structure of the cosmos and the movement of celestial objects within it. The astronomical book of 1 Enoch was preserved in its most complete form in the Ethiopic manuscripts of the text and was partially confirmed by the Dead Sea Scroll fragments found at Qumran, which demonstrate that the astronomical book was in circulation in the 2nd century BCE and was treated as an authoritative text by the Qumran community. The astronomical book describes, through the voice of the archangel Uriel instructing the patriarch Enoch, the movements of the sun, moon, and stars in systematic detail. What is remarkable about the astronomical book in the context of tonight's report is its treatment of celestial objects that do not follow the established rules. The text describes the regularly moving celestial bodies in careful detail: the sun's annual journey through its windows, the moon's monthly phases, the stars that rise and set on schedule, and then it describes what happens when the established order is disrupted. Chapter 80 of 1 Enoch contains a description of a future period of disruption in which the regular celestial order fails. Stars deviate from their commanded paths, the seasons become irregular, the cosmic schedule that the astronomical book had described as fixed and reliable ceases to operate on schedule. The specific language in Chapter 80, translated by George Nicholsburg in his 2001 Hermeneia commentary, a work of careful Ethiopic scholarship published by Fortress Press, describes stars that transgress their order, that is, stars or celestial objects that deviate from the established pattern of motion that the astronomical book had described as the proper cosmic order. In the context of the astronomical book's systematic description of regular celestial motion, a star that transgresses its order is precisely what an interstellar object is. An object that does not follow the order of the solar system's established orbital mechanics, that arrives from outside, that moves across the sky on a path that no solar system object follows. The astronomical book of 1 Enoch is not describing interstellar comets in the modern scientific sense. It is describing a disruption of the established celestial order in the language of Jewish apocalyptic tradition, where disruption of the natural order signals the approach of a period of judgment or change. But the underlying observational awareness that the sky's established patterns can be violated by the arrival of something that does not follow those patterns is real and is encoded with sufficient specificity in the astronomical book to make the structural parallel to interstellar object science notable. The Dead Sea Scrolls fragments of 1 Enoch's astronomical book, found in Cave 4 at Qumran and published in the Discoveries in the Judean Desert series by Joseph Milik in 1976, demonstrate that this text was actively used by a Jewish community living in the Jordan Valley in the 1st and 2nd centuries BCE. They were living in one of the most seismically active zones in the ancient Near East. They were also living under extremely clear desert skies that would have given them exceptional conditions for naked-eye astronomical observation. Whatever sky phenomena they actually observed with their own eyes in those desert skies was the empirical foundation for the cosmological framework encoded in the texts they've preserved. 3i, Atlas, was not visible to the naked eye, but the stars are. The regular motion of the planets is. The occasional appearance of a bright comet is. Any community of careful sky watchers living under clear desert skies for centuries would accumulate observational knowledge of the regular celestial order and would notice when something deviated from it. The astronomical book of 1 Enoch is the product of exactly that accumulated observational knowledge, encoded in the available theological and literary framework. The book of Enoch says, "The sky has an order, and when that order is violated by objects that transgress their commanded paths, it matters." The 3i Atlas dataset says, "The solar system has an orbital order, and 3i Atlas did not follow it, because it came from outside. The structural parallel is precise. These are the records. They are all in archives that are publicly accessible. The ancient record and the modern record both describe the same fundamental phenomenon, the arrival in the observable sky of something from outside the established order from different directions, in different languages, with different instruments and different conceptual frameworks. The convergence across these records is a convergence of observation, not of interpretation. The observation is shared. The interpretation remains yours." Tonight's report is filed on the 31st of May 2026. 3i Atlas is receding from our solar system at 58 kilometers per second relative to the Sun. It will not slow down. There is nothing in the outer solar system large enough to significantly alter its trajectory, and our Sun's gravity, which has been decelerating it since it entered the inner solar system, has already released its grip. The comet is past its aphelion crossing. It is on its way out. In 50 years, it will be beyond the farthest reaches of the Oort cloud, if it passes through the Oort cloud at all. In 1,000 years, it will be in interstellar space again, carrying its deuterium-rich water ice and its pre-solar chemistry back into the dark between stars, where it will travel until something else intercepts it if anything ever does. What remains is the record. The full data set from more than a dozen NASA missions and multiple ESA spacecraft, now in NASA's permanent public archive, is freely accessible. The Nature Astronomy paper on 3I Atlas's water deuterium ratio, authored by a team led by Luis Salazar Manzano at the University of Michigan, is published in the journal Nature Astronomy with the DOI 10.1038 S41550 026028 505. The University of Michigan origin study tracing the comet's trajectory through the Milky Way using Gaia stellar position data is published and available. The 13th of May, 2026 dual spacecraft UVS imaging paper from the ESA JUICE and NASA Europa Clipper instruments is available at phys.org and through the Journal of Record. NASA's full 3I Atlas data archive is accessible at science.nasa.gov. Several specific monitoring items remain open as this report is filed. The ESA Comet Interceptor mission, currently in development, will be ready for deployment within the next few years. Its scientific case has been substantially strengthened by 3I Atlas's passage. When the next interstellar object is detected and the improving sensitivity of wide-field survey telescopes, including the forthcoming Vera C. Rubin Observatory in Chile, means that detection rates are expected to increase significantly in the coming decade. The response time and the available instrumentation will be substantially better than what was available for Oumuamua in 2017. For 3I Atlas in 2025, the response was already qualitatively better than for Oumuamua. The dataset is vastly more complete. For the fourth interstellar object, if it arrives in range of Comet Interceptor, the dataset will be better still. The Vera C. Rubin Observatory, formerly the Large Synoptic Survey Telescope, is designed to conduct a 10-year survey of the visible sky with unprecedented depth and cadence. It will detect hundreds of millions of objects that current surveys miss. Its sensitivity to faint, fast-moving objects means that interstellar comets like 3I Atlas, which was detected only weeks before its closest approach to Earth's orbit, could be detected months or even years in advance by Rubin. The first light timeline for Rubin's full survey operations has been ongoing, and when it reaches full operations, the sky will be surveyed in a fundamentally different way than it is today. The question that the 3I Atlas dataset poses for planetary science, in its most direct form, is this. If interstellar objects carry chemistry from pre-solar molecular clouds, if they carry water with deuterium ratios 30 times higher than any solar system comet, what does that tell us about the distribution of water and complex chemistry across the galaxy? Our own solar system's comets were long thought to be possible contributors to Earth's water through a history of impacts during the late heavy bombardment period approximately 4 billion years ago. If interstellar objects also pass through the early solar system, and given the estimated rate of interstellar object detections in the current era, there is strong reason to believe they did. Then the chemistry they carried is part of the chemical history of the solar system that produced us. The deuterium fingerprint of 3I Atlas is not just a record of the conditions in one cold molecular cloud in the early galaxy. It is a potential contribution to the chemistry that made Earth habitable. That is a claim in the scientific literature that is not yet settled and is not close to being settled. It is mentioned here not as a conclusion but as an open question on the record, because it is the kind of question that the 3I Atlas dataset will be used to address over the next decades. The full photometric, spectroscopic, infrared, and ultraviolet dataset from more than a dozen spacecraft and ground-based observatories is now available to any researcher with internet access. That is an extraordinary thing. The third interstellar visitor in human history passed through our solar system was observed with more instruments than any previous interstellar object by an order of magnitude, and the full result of that observation is now in a freely accessible public archive. The ancient skywatchers who built the Babylonian omen tradition across centuries of systematic observation, who maintained the Hopi cosmological tradition across generations of oral transmission, who compiled the Chinese guest star records through 2,000 years of dynastic history they were doing in the forms available to them, the same thing that NASA's archive represents. Watching, recording, making the record available for those who come after. This channel exists to do that cross-referencing work, to take the modern archive and lay it alongside the ancient archive and let both speak. The 3I Atlas dataset is now in the archive. The Hopi Blue Star Kachina tradition is documented in Waters' 1963 book, available in university libraries worldwide. The Oumuamua Enlil tablets are in the British Museum and the Louvre and have been available in scholarly translation for decades. The Voluspa and the Prozeda are in every major library in the Northern Hemisphere. The Chinese guest star records are in the dynastic histories, which are translated and available. Both archives are real, both are accessible, both describe, in their different vocabularies, the arrival of something from outside the expected order of the sky. The parallel does not require supernatural explanation. It requires only the recognition that human beings who watch the sky carefully across many centuries tend to notice the same things and encode them in the available language. An interstellar comet is something that has always been arriving and departing in the space between stars. The ancient record noticed. The modern record has now measured. If tonight's report gave you something the standard science briefing did not, if the Hopi Blue Star tradition, if the Babylonian omen framework, if the Norse distinction between the ordered sky and Utgard, if the Chinese guest star record added something to your understanding of what 3I Atlas represents, then this channel is doing its work. We file every night. The monitoring record does not pause. Tomorrow's report will have a new event, new data, or a new layer of the archive that deserves examination. We will be here. Subscribe if you want to be here too, and drop your location in the comments tonight. Tell us where you are watching from, and whether you ever looked up and tried to see 3I Atlas in the months when it was still traceable by the telescopes. Your observation is part of the record too. We continue to monitor. We will report again at last light. There is a final element of tonight's monitoring picture that deserves mention before this report closes. The Vera C. Rubin Observatory, which has been under construction at Cerro Pachon in Chile, is designed to conduct the Legacy Survey of Space and Time, a 10-year, wide-field optical survey of the southern sky that will produce the deepest and most comprehensive optical map of the sky ever made. When it reaches full operations, it will be capable of detecting objects substantially fainter and faster moving than current survey systems. The theoretical estimates for interstellar object detection rates by Rubin, published in multiple studies in the years following the 3I Atlas discovery, suggests that Rubin may detect tens or even hundreds of interstellar objects over its 10-year operational lifetime, compared to 3 in the decade of less sensitive surveys preceding it. If those estimates are correct, the field of interstellar object science, which currently has a dataset of 3 objects, will within a decade have a dataset of potentially dozens. The compositional diversity that the 3-object dataset already reveals, Oumuamua with its anomalous acceleration and no detected coma, Borisov with its relatively conventional cometary behavior, and 3I Atlas with its extreme D/H ratio suggests that the galaxy's interstellar object population is heterogeneous in ways that a larger sample will begin to characterize. Properly, that characterization is the science of the coming decades. The record that 3I Atlas left in NASA's archive is the foundation on which it will be built. Tonight's report is a contribution to the documentary layer of that record, to the practice of watching, naming, and cross-referencing that connects the modern scientific archive to the full depth of the human observational tradition. The Babylonian astronomers who recorded unusual celestial events in the Enuma Anu Enlil were contributing to a record that outlasted their civilization by 2,000 years. The Hopi elders who transmitted the Blue Star tradition to Frank Waters in the early 1960s were contributing to a record that their tradition had been preserving for a millennium. The Chinese astronomical observers who recorded guest stars in the dynastic histories were contributing to a record that is still being used by modern astrophysicists to date. historical stellar explosions. These are the traditions this channel exists to cross-reference against the modern scientific record, not to claim they predicted specific events, to document that human beings across many cultures and many centuries have been watching the same sky and arriving at structurally similar recognitions about what it contains. 3I Atlas is gone. The monitoring file is closed in the sense that no further observations will be made. It is beyond the reach of any instrument. But the archive is open, permanently, and the science it contains will not be exhausted in any of our lifetimes. The data is on the record. The interpretation belongs to you. One additional element of the 3I Atlas dataset that warrants mention in tonight's monitoring file is the comet's behavior as it receded from perihelion. In late 2025 and early 2026, as 3I Atlas moved outward from its closest approach to the Sun, its coma evolved in ways that were carefully tracked by the final observational campaigns. The SphereX February 2026 data showed changes in the coma composition relative to the December 2025 observations as the comet cooled and the heating from the Sun diminished. The more volatile ices began to quench their sublimation. The water production rate, as measured by the Europa Clipper and JUICE ultraviolet spectrographs in May 2026, was lower than at perihelion but still detectable at the time of those final observations. This declining outgassing signature is consistent with normal cometary behavior during recession, the comet's nucleus cooling, the sublimation rates dropping, the coma thinning. The comet was dying down, not collapsing. By the time it reaches the distances where the outer solar system begins to shade into the interstellar medium, where the heliosphere weakens and the interstellar magnetic field begins to dominate, there will be no active outgassing. The surface ices will have recooled. The comet will be dormant again, as it was for the 11 billion years before it entered our solar system. That dormancy is, in some sense, the default state of 3I Atlas. Active, coma-producing cometary behavior is a brief episode in its existence, triggered by passing close to a star, suppressed again when the star's heat is left behind. It has been dormant for essentially all of its history. The episode of activity triggered by our Sun was brief enough in the comet's total lifetime to be essentially undetectable in any long-term accounting. But it was enough to reveal the deuterium fingerprint, enough to reveal the organic chemistry, enough to trace the origin to a cold molecular cloud in the early galaxy. The science extracted from 8 months of observation, from a comet that has existed for 11 billion years, is already changing the picture of what the galaxy's interstellar medium contains. The archive that 8 months produced will be analyzed for decades. We monitor what the instruments show. Tonight, the instruments show an empty sky where 3I Atlas was. The archive shows everything the instruments found while it was here. Both are the record. Both deserve to be kept. The monitoring picture tonight is, in the most precise sense of that phrase, a closed file on one object and an open file on the category it represents. 3I Atlas has departed. Its record is in the archive. The category interstellar objects passing through the solar system remains active. The Vera Rubin Observatory will change the detection rate. The instruments that will observe the next interstellar object will be more capable than the ones that observed 3I Atlas. The scientific community has now had 3 opportunities to practice the response to an interstellar arrival, and each practice has been better than the last. From Oumuamua in 2017, detected too late, uncharacterized compositionally, leaving only anomalies and questions to Borisov in 2019, detected with adequate warning, characterized broadly with a familiar cometary profile to 3I Atlas in 2025, detected early enough for a multi-year campaign, characterized with the most sophisticated instrument suite ever applied to an interstellar object, and leaving behind a dataset with a compositional signature that no one predicted, and that changes the scientific picture of what the galaxy's interstellar medium contains. Each iteration better, each archive more complete, each dataset adding something to what was known before. This is how science works at its best. Not in single definitive discoveries, but in accumulating precision, In a monitoring tradition that improves its instruments and its response protocols with each new observation, and that places every result in a publicly accessible archive so that future researchers can build on what came before. The Babylonian astronomer priests, who recorded their celestial observations on cuneiform tablets, were contributing to an archive that outlasted their civilization. The Hopi elders who transmitted the Blue Star tradition across generations were contributing to a record that outlasted many of the specific social structures through which they transmitted it. The Chinese astronomical observers who wrote their guest star records into the dynastic histories were contributing to a record that is still useful 1,000 years later. The NASA missions that observed 3I, Atlas, and deposited their data in the public archive are contributing to a record that will be useful decades and perhaps centuries from now. Last Light Bureau files every night because the monitoring tradition requires it. The sky produces events. Events require witnesses. Witnesses must record. The record must be kept. What the instruments show, we report. What the historical record demonstrates, we document. What the ancient layer illuminates, we lay alongside both and let you read. This is the work. Tell us where you are watching from tonight. Tell us whether 3I, Atlas, meant anything to you when it was in the news, whether you followed the observations, whether the idea of a comet from 11 billion years ago and from a pre-solar molecular cloud produced any response in you that science alone did not fully account for. Your observations belong to the record too. Subscribe if you want to be here when the next report files. The instruments are running, the file stays open, we continue to monitor, we will report again at last light. A note on the scale of what tonight's briefing has attempted to assemble, the 3I Atlas dataset represents the work of thousands of scientists, engineers, and mission controllers at NASA, ESA, the University of Michigan, the ALMA Observatory, and dozens of other institutions worldwide. The ancient archive it was placed alongside tonight represents the accumulated observational and interpretive work generations of Babylonian astronomer priests, Hopi oral tradition keepers, Norse saga composers, and Chinese imperial astronomers across spans of time that dwarf the modern scientific era. The parallel between them is not a comparison of quality or of certainty. The modern dataset is quantitatively more precise than anything the ancient tradition produced. But the modern dataset and the ancient archive are asking the same question. What is the sky? What arrives in it from outside? And what does that tell us about the structure of the universe we inhabit? The answer in both archives is the same. The universe is larger than the ordered region we can see from here, and occasionally something from the larger universe arrives in our portion of it, carrying its own chemistry and its own history and its own record of conditions that our instruments, if they are good enough, can read. We continue to monitor. We will report again at last light. The monitoring record for tonight includes the NASA 3I Atlas Public Data Archive at science.nasa.gov, the Nature Astronomy paper DOI 10 1038 S41550 026028505, the ESA JUICE and NASA Europa Clipper UVS dual imaging paper at phys.org, published the 13th of May, 2026, and the University of Michigan Origin Study tracing the comet's galactic trajectory using Gaia satellite data. All sources are real, findable, and available to any reader. The record stays open.